Number 7 says X is the number of broken eggs in a randomly selected carton with a dozen store brand eggs at a certain market. Suppose the probability distribution is as follows: 65% of the eggs, or 65% of the cartons have no broken eggs, 20% have one broken egg. And if this is all the values, then we know that all of these things here have to add up to be 100%. So this one is going to be 0.01. The probability of 4 broken eggs is pretty remote, and apparently we never have 5 or 6 or 7 or 11 broken eggs. Part B says calculate the probability y is less than or equal to 2. So what I'm looking at here is this section, less than or equal to 2. So it's 0.65 plus 0.20 plus 0.1. If this confuses you a little bit, maybe put a 0 after that so you don't make a decimal place error. So that's 65, 75, 85, 95% of the eggs or cartons have at most 2 broken eggs. Now it says, what's the probability y is less than 2? So now this one right here doesn't count because that's exactly equal to 2. So it's 0.65 plus 0.20, which is 0.85. And it wants you to wonder about why is that different than what I got before? Or in particular, why is it that this equal sign matters? Well, the equal sign matters because we have a discrete distribution. So the distribution is discrete as opposed to continuous. Or put another way, the probability x equals 2 is not 0. In a continuous distribution, the probability that x equals something specific is 0 because you're just dealing with the area of a line. And in a discrete case, the graph would be a histogram, not some fluid density curve like on a continuous one. Letter D says, what's the probability we have at most 10, or sorry, we have exactly 10 unbroken eggs, which means we have exactly 2 broken eggs, which is 0.10. Be careful here, they kind of switched gears on you with how they're doing it. The next one says at least 10 eggs are unbroken, which means I have either no broken ones, or 1 broken one, or 2 broken ones. X equals 2. And so that's going to be the 0.95. Just like I did on part B, it's just worded differently. Now letter F says, what's the expected number of broken eggs per carton? What's the expected number of broken eggs? That's the same as the mean. And you might not remember this formula, but you can go and look on your formula chart. And this formula right here underneath the probability heading says the expected value for x, or the mean of x, is the sum of each number times its respective probability. So here's what that means for this problem. The expected number is going to be 0 times 65% plus 1 times 20% plus 2 times 10% plus 3 times 4% plus 4 times 1%. And you multiply and add all that together, and you can trust me, you get 0.56. So on average, there's 0.56 broken eggs per carton on average. Now letter G says, what's the standard deviation? And maybe you noticed when you looked at the formula chart, it says right here, here's the formula for variance. So I can find the variance and then take the square root of it. So it's each number minus the mean squared times its probability. And that seems really complicated, but really it's just repetitious. So here's what it is. The variance is what I'll find first, and then I'll square root it. The variance is going to be 0 minus 0.56 squared times 65%. plus 1 minus 0.56 squared times 20% plus 2, hang on, minus 0.56 squared times 10% all the way till I get to the 4 minus 0.56 squared times 1%. And again, you can trust me here that the answer is 0.8064. And if I wanted to find the standard deviation, like they've asked for here, I can just take the square root of 0.8064 to get 0.898. Now that's how you use the formulas. That may seem a little bit tedious, but let's see if we can work this on our calculator a little more efficiently. On this problem, how many variables are there? One variable. This is a big issue. It's not 5 variables, it's not 2 variables, it's one variable because I said, hey, carton of eggs, how many eggs are broken? One question, one variable. And so if I put this stuff in my calculator, I'm going to put it in my calculator like this. So I put the y's in L1 and the probability of y's in L2. And then I can do one var stats on this information. So I go stat, calc, one var stats. The list is in L1. And how often those things occur, the frequency is in L2. So when I hit calculate, chicka chicka whir, there's my mean, 0.56. There's my standard deviation, 0.89799. And a little more efficient way to get those last two answers.